So in the part one of this playlist, machine translation, I was explaining a beautiful paper of Yashio Bengio about using sequence to sequence with attention, which we love LSTM and those things. But now we want to improve state of the art by taking advantage of syntactic structure, because a sentence is not just a sequence of words. It has a structure. It has syntactic structure. It has dependency structure. And so we should take advantage of that in order to improve these machine translations. And so now if you're using dependency-based approach, your approach becomes universal. And so today I'm going to be representing this beautiful paper in 2016, which was the source of inspiration for many great authors such as Puya in Monash University, and also these people in Facebook. So I will explain this article in the next lecture. So let's focus on this article in 2016 by people in Tokyo, Japan. So most of the existing neural machine translation models focus on the conversion of sequential data and do not directly use syntactic information. Especially even in language modeling, look, very few people are using this beautiful syntactic information. That's why some of their models may not be good in comparison to those who use syntactic informations. So their approach is, we propose a novel end-to-end syntactic neural machine translation model, extending a sequence-to-sequence model with the source-size phrase structure. And our model has an attention mechanism. It's just attention mechanism, but we are generalizing to tree-based, like ThreeLSDM, the great paper of Christopher Manning. So their data set is, for example, English to Japanese data set, this data set. And this is an example. So we need an alignment, because we need to know how to, if you have seen my previous lecture, part 1 in machine translation, you need to attend, because it's alignment. It means sometimes some words in the input should be aligned to or focused to some words in the output. So the energy becomes high if this alignment is high. For example, this is a word in Japanese, but you see it has 2 words in English. So that's challenging. So the only thing that can help us is a syntactic representation, syntactic information, let's say. So figure 1 shows a pair of parallel sentences in English and Japanese. And English and Japanese are linguistically distant, and in many respects. And so this is a neural machine translation. So they represent it by just an encoder. A recurrent neural network could be anything, could be LSTM, GRU, anything. So represented by this encoder, and for a decoder, we can use, these are traditional things that we do in the default neural machine translation. Then even if we use attention, this is how maps the hidden states of encoder and hidden states of decoder to produce this alpha. And we use this alpha to produce this context. And we use this context D, we concatenate it with the hidden representation of decoder to get SJ tilde. And just a softmax over that, over a linear layer over that, gives us what is the words that are generated as a translation. For example, in English to Japanese, this Y is the Japanese words that are generated. What is the probability of each word at a given time? So the attentional encoder decoder model is what I have explained in the previous lecture. But now we want to generalize this to say, instead of this, you see this sequential approach, we want to say, to make it a little bit like a graph, like a tree, like ThreeLSDM is a good example, like that. And this is their approach. I mean, the structure of each of these is like this. I, for example, is input gate, F is forget gate, and C are your memory cells, that those long-term things, and H your hidden representation, which represent short scales, short lengths, context, and so here you have different K, because for example, each hidden state here, you give 2 inputs to that. Of course, it depends on the structure of that. So if you have seen my lecture on ThreeLSDM, of great paper of Christopher Manning, you see this is an alternative to that. It's just the inside implementation is a little bit different, but it's almost the same. So we initialize the decoder using like this idea, and the attentional mechanism. So this part is exactly the same part in the previous lecture. So the main innovation in this lecture is adding this extra term which represent the phrases. Because if you have because a binary tree has n-1 phrase nodes if the tree has n leaves. So the rest of that is here. So it's the same intuition. I mean, you have alpha again like before, but here for phrases you sum over those phrases. So you see, it's just generalization of that. And because the main problem challenge is on decoding, they use sampling based to have a faster approach. Oh, by the way, I think you have seen my playlist for word2vec that I use. We have different issues for those softmax, which you should marginalize. You should sum over all vocabularies. So that's why I explain negative sampling for word2vec, and also hierarchical softmax. So these 2 ideas make your softmax much faster. And as I've said several times, that hierarchical softmax is the future. In future, people will use hierarchical softmax instead of just a simple softmax. Especially if you have 1 million words, if you have a large amount of, let's say, categories, even in computer vision. If there are lots of categories in classify, or if you have seen my playlist for extreme classification. So you see these hierarchical softmax idea. This negative sampling is quite easy. Just use sigmoid and you have some positive labels and negative things, and it's not very intuitive. I mean, it is not. For example, in our brain, it doesn't use negative sampling, but our brain uses hierarchical softmax with high probability because our brain is based on a graph structure, a Markov chain, and a simple graph is a tree. And hierarchical softmax is a tree. It says if this is high probability, go left. If this is high probability, if it goes right, then you multiply all of these probabilities because they are independent, and you see what is the probability of a given token. And this is another example for translation of a short sentence and attentional relations. You see how beautifully this English is aligned with the Japanese one. If you are using this syntax information. So we have different alpha. I explained the formula for that, the same intuition. This is another example, different alpha, your reference and your translation, end of statement. And there are different measures, to say if your machine translation algorithm is good. One of them is bilingual evaluation understudy. The other one is RIBES, rank-based intuitive bilingual evaluation scores. These scores are really important. That's why in their article they write it, they measure it with that for different models.